Welcome to this video on structural boundary value problems. This is one of several videos in a short course on structural members posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. When we analyze structures, such as buildings and bridges, we first create idealized models, either for use in hand calculations or for computer analysis. The structural models are created by discretizing the structure into individual but interconnected structural members. Several types of structural members are available. Two-dimensional continuum members carry load only in their plane. Plates carry load perpendicular to their plane. Shell elements carry load both in their own plane and perpendicular to it. However, the most common types of structural members are truss, beam, and frame members. They are one-dimensional members in the sense that their longitudinal dimension is much larger than the cross-section dimensions. Truss members, sometimes called axial rods, carry only axial force in the longitudinal direction. Beam members carry load perpendicular to the longitudinal axis by means of internal bending moments and shear forces. Frame members extend beam members by including axial force. We can also include torsional deformation for such members. An important choice when employing truss, beam, and frame members is the type and dimensions of the cross-section. Circular, wide flange, and rectangular cross-sections are available. Furthermore, for the so-called thin-walled cross-sections, they can be either open or closed. More details about cross-section analysis are provided in a short course on cross-section analysis posted at terje's Toolbox. That is because we can often separate the analysis of the member from the analysis of its cross-section. It is the analysis of the full member that is the subject of the present course. From a mathematical viewpoint, a structural member is a boundary value problem. This means we formulate certain ingredients and combine them into the differential equation that governs the behavior of the structural member. When we add boundary conditions, such as clamping the member with a fixed support at some location, then we have a properly formulated boundary value problem with a unique solution. The solution typically includes the stress, strain, and displacement caused by an externally applied load. Boundary value problems like this, including truss, beam, frame, plate, and shell members, are the bread and butter of solid mechanics. And solid mechanics generally consists of three types of governing equations. They are mentioned in red rectangles on this slide, and they are equilibrium, material law, and kinematic compatibility. It is those three ingredients that we combine in order to formulate the differential equation for a structural member. Equilibrium equations express how the external load relates to the stress at each point in the material that the structural member is made of. The material law equations express the relationship between stresses and strains. The kinematic compatibility equations relate the strains inside the material with the global displacements of the structural member. Before we leave this slide, two additional points are made. The first is that there is a continuum assumption behind all the equations of solid mechanics. As mentioned in the short course on stress posted at terje's Toolbox, this represents an idealization of materials that in reality are more grainy. However, it comes with the benefit that we can work with stresses and strains, which are useful but in reality somewhat abstract concepts. The second point relates to the left-hand side of this slide, namely the equilibrium side. For truss, beam, and frame members, we add stress resultants in the path from load to stress. Stress resultants, such as a bending moment, is related to stress via equilibrium equations. Additional equilibrium equations relate the stress resultants to the externally applied loads. The next slide shows a preview of a boundary value problem that is addressed in another video in this short course on structural members. It is Euler-Bernoulli beam bending that is addressed here. The ultimate goal is to link the externally applied load Q with the resulting displacement, W, as you see here. Equilibrium equations relate the external load to the bending moment. Another equilibrium equation relates the bending moment to the axial stress in every fiber of the beam. The material law is represented by Hooke's law at the bottom. The kinematic compatibility equation relates the strain at every fiber of the material in the beam to the external displacement. You will see the ingredients of many boundary value problems for structural members organized like this in terje.civil.ubc.ca Toolbox. The next slide gives a preview of matrix structural analysis, or the computational stiffness method, covered elsewhere in terje's Toolbox. The organization of the boundary value problem is the same. Equilibrium equations are on the left-hand side. Kinematic compatibility equations are on the right-hand side. Forces, denoted by F, and displacements, denoted by the letter U, are linked in the middle via stiffness matrices, which represents the material law in this case. The next slide shows another example of the way boundary value problems are organized and visualized in terje's Toolbox. This time it is the connection between forces at the element level, cross-section level, and material level from nonlinear structural analysis that is displayed. In such problems, it is often the material law, with yielding and hysteretic material behavior, that is of primary interest. The next slide is hard to understand at first, but it shows that the differential equation is not the only way to formulate the complete boundary value problem. However, the differential equation is important, and it is referred to as the strong form of the boundary value problem because it requires the full satisfaction of equilibrium, material law, and kinematic compatibility at all points in the structural member. The equations shown here are for beam bending, and you may recognize the differential equation from an earlier slide. Each prime symbol means one derivative with respect to x. The differential equation is here written in residual form, which means that everything is placed on the left-hand side, with a zero on the right-hand side. In a course on the finite element method or energy methods, you will learn more about the various forms of the boundary value problem. As a preview, you see here that we multiply the differential equation with a function, here called a weight function, followed by integration of that equation over the entire length of the beam. The result is the so-called weighted residual form of the boundary value problem. It is a valid form, but it is also a weaker form than the differential equation. We no longer require pointwise satisfaction of equilibrium, material law, and kinematic compatibility. Rather, we now require the differential equation to be satisfied in an integrated sense. Next, we carry out integration by parts in order to have the same order of derivative on the displacement, W, and the symbol delta W, which can now be interpreted as a virtual displacement. The result is an expression of the principle of virtual displacements and is called the weak form of the boundary value problem. This form can also be obtained by starting with the principle of virtual displacements, which represents equilibrium in an integrated average sense, and substituting material law and kinematic compatibility. The fourth form of the boundary value problem is the variational form. It is necessary to learn variational calculus in order to work with this form, which is an expression of balance of energy. Strain energy is here on the left-hand side and potential energy from the external load is on the right-hand side. The material presented on this slide is outside the scope of this short course on structural members. However, it gives a glimpse into the foundations for advanced structural analysis methods, such as the finite element method and energy methods. Thanks for watching this video. Please visit terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.